Hello. In previous video we were reading about finite squarable potential. This is continued part. From starting we consider a figure, that is figure of potential, and after we applied Schrodinger wave equation to study dynamics of the particle, and by applying boundary conditions we reach up to this equation, which was K2 tan K2A upon h cut, this is 2, K2 tan K2 upon 2 is equal to K1, first one, and second K2 cot K2A by 2 is equal to minus K1. These two equations we have achieved in previous video. Now in this video we have to solve these equations, and to solve these equations we will use graphical method. Graphical method for the solution of these equations. So to obtain these equations you must go through previous video of finite squarable potential, and if you have done, then start from here. So how to solve using graphical method? Let us see. Here the value of K1 and K2, as we know that K1 is under root 2m V naught minus E upon h cut. This was K1, and K2 is equal to 2me upon h cut. So these are the values of K1 and K2. So from here we can see that tan K2A upon 2 is equal to K1 by K2. So when you will divide these both, what we get? We get 2m V naught minus E upon 2me, here upon h cut, here also upon h cut. So h cut will be cancelled out and 2m also cancel out. What we have? We have now under root V naught minus E upon E. In more better way, writing this V naught upon E minus 1. This is. Now introduce alpha n square, that is alpha n K2A by 2. So alpha n square is K2A by 2 whole square. Now what is K2? K2 is under 2m upon h cut. So this is K2 square, A square upon 4. So K2 square, A square upon 4. kt square is 2me upon h cut square a square by 4. This is 2 to the 4. So, m a square upon 2 h cut square e, writing here n, so writing here en. So, this is also introducing r square, which is ma square v naught upon 2 h cut square. This m square upon 2 h cut square v naught r square, and for n alpha n square. This we have introduced. So, when we divide these from here, if we divide this both, that is finding r square upon alpha n square, this by this, what we get? V naught by E. It means that we can put this value here, V naught by E. So, writing here now in introduced terms, r square upon alpha n square minus 1. Writing better. So, under root r square minus alpha n square upon alpha n, and this tan k2a. So, this will be now tan alpha n, because alpha n is k2a by 2. So, this will become tan alpha n. This will become tan alpha n. So, tan alpha n is equal to what? This. As same for this, for cot, this will be minus k1 by k2. So, same process we will do for from here, cot k2a by 2 is equal to minus k1 upon k2. So, for k1 upon k2 is equal to this. So, this will be only minus sign, and this will be cot alpha n. So, writing cot alpha n is equal to minus of this quantity. So, this to this and this one. So, what are here? Writing that also of tan alpha n. This is under root r square minus alpha n square upon alpha n. Now, look, on LHS we have trigonometric functions. And this part on RHS, this we have circle of radius r. This part constant by n, it is alpha n. So, we can shift alpha n this side, that is this alpha n can be shifted here. So, just remove from here, writing alpha n by cross multiplication, as same from this side also alpha n. So, now using these we will draw now graphical method. So, graph will form using these equations. So, let us see how the graph looks like. So look now graph, is taking alpha n, which is 0, pi by 2, is pi, 3 pi by 2, interval of pi by 2, 2 pi, 5 by 2, pi, 3 pi, and so alpha n. Bring here this lines. This dotted lines. Okay. Now we will plot graph of tan and cot. So plotting now. Very smartly now. Let's plot it. These are of alpha n, tan alpha n. Also of cot alpha n. So this region. This is of alpha n cot alpha n. So, this is of LHS. Now, of RHS, for that we will draw very smartly for radius of the circle. This one. Okay, drawing by blank. This one, radius of the circle. So, we may vary this So, these are the radius of the circle, circular part, this one and this one, and more we can draw. So, after drawing these quadrant part of the circle of radius r, we get these intersection points. Look clearly, this here, this is at 10, this one, as well here. Here also. So, radius of these circles is under root r square minus alpha n square. This circle also, and this is by these equations which we have got, minus alpha n cot alpha n square root r square minus alpha n square. Graph intersection points and these points, these blue points. So, these are the solutions of this equation, intersection of this and this. Also, alpha n, tan alpha n, r square minus alpha n square. So, the solution of these equations are shown by these black dots here. This is for different circles. Here n is equal to 0 for first, here also this is for n is equal to 0, for here n is equal to 1, for here n is equal to 2, and for this n is equal to 3. And here these are r square, this is gma square v naught upon 2 h cut square, because this smaller circle and this tan alpha curve, we get one bound state. Due to this intersection, we are getting discrete set of solution. So, for a small circle and alpha and n, we get one bond state n is equal to 0, and for larger we get two bond state. For this equation here and for this equation here. So, what will be the number of solutions will depend obviously on radius of the circle. If solution depends on radius of the circle, it means that it will depend on depth of the potential and also width of the well. So, more broader, that is more broader is high and more deeper, that is V naught is large in this figure. This was 0, a by 2 minus a by 2 and V naught. Remember this figure? So, in this figure if we increase this more broader and more deeper, that is a greater and V naught greater. So, we get large value of R. So, more R, greater R, we will get greater solution, that is more solutions. So, number of solution, or we may say number of bound states, depends on R, which depends on A and V naught. So, this is how there is variation in bound states, which depends on A and V naught. Also, to note one point, whatever is the value of V naught, that is how minimum V naught is, we will get value of R. So, what is the minimum value of V naught? Whatever V naught for small values, we get R, and when we get R, we will get this intersection point. It means that we will get at least one bond state, no matter how V naught, how much V naught is small. And for n states, for n bound states, we have general formula of R n pi by 2. N pi by 2, n is equal to 1, pi by 2, n is equal to 2 pi. So, n pi by 2, and using this here we get V naught also. So, R square is n square pi square by 4, putting this value here, m square V naught upon 2 h square, n square pi square upon 4. So, V naught will be V naught pi by 2 whole square, and this 2h cut square shifted here upon m square here, and n square. So for n bound state we will have this r and this v naught. Also see that this is case if v naught is infinite, it means that r tends to infinite from this relation, and from this relation tan alpha n tends to infinite, and also cot alpha n tends to infinite. So we get asymptotes at alpha n is equal to n pi by 2. For this alpha n is 2n plus 1 upon 2 pi, where the value of n is 0, 1, 2, so on. And for this we have value of alpha n pi, where n is 1, 2, 3 and so on. So on combining these we get this alpha n. So we get asymptotes here, we can see in the graph. So now putting here value also, alpha n square is equal to n square pi square by 4. And what is alpha n square? This we have just assumed that alpha n square is m a square upon 2h cut square en. So we will put, this is equating this alpha n square to this value, m a square upon 2h cut square en. Now using this we will find en. What is en? From here, n square pi square h cut square upon 2m a square, and this is the energy expression for the infinite well. So we get using finite well also. That's it.